Okay, so we have this car, is problem 14.5. We have this car traveling towards a pier, and really to stop this car from driving off the pier into the water, there is this barrier here. It's called a barrel barrier. And really it acts like the idea is that it acts like a spring to slow the car down. Okay? So Google it, find out more about how this thing works. If the relation between the force and the deflection of the barrier is given by this, right? This is it. F equals 800 times 10 to the 3, x to the half. So this is the spring force. Okay, in a sense. It's a kind of a spring force. What you notice is that it's not linear. Right? We're used to a spring force that looks linear. So this is a non-linear force, which means that it's not constant. Okay? So this car is driving and then it rams into this barrel barrier, and this barrel barrier applies this force to the car to slow it down. Okay? Alright, so determine the car's maximum penetration into the barrier. Determine the maximum penetration into the barrier. The car has a mass of 2,000 kilograms and is traveling with a speed of 20 meters per second. Okay, so we've got force information, we've got velocity information, and we want to know the maximum penetration. Okay, so if we take that, say, as x equals 0, how far does the car go into this barrier until it stops? Okay, so this will be our total distance x before it stops, and x equals 0 there. Okay, so because we've got these three, we've got force, velocity, and displacement, distance, we can use principle of work and energy. Okay, so what is T1? T1 is half mv1 squared. And what is T2? Well, T2, we know that V2 is 0 because it comes to a rest, so we know that this is 0 on the right hand side. But now, so we'll get to this, we've got M, we've got V, right? There's the mass, there's the velocity. Now, what are all the forces acting on the car during this time from there to there? The only force, well, we know that there's the normal force and weight. Okay, but we're not really interested in the vertical direction. We're interested in the horizontal direction, and we know that this force is slowing the car down, so it has to be to that direction. There is that force. It's given by this nonlinear relationship. But now remember, this is work. So there's the integral of this 800 10 to the 3 x to the half dx. Okay, remember, it needs to stay, because it's a non-constant force, it needs to stay inside the integral. Okay, although of course you can remove this from the integral, you can take that outside, but because it's not constant, we need to keep it inside the integral. So just go back and look at the previous videos. Now the question I have, so that's the first thing. The first thing to note here is that it's a non-constant force, so this x to the half dx, or the x to the half, needs to stay inside the integral because it's not constant. Now the second question I have, or the second point, is this going to be plus, is it going to be positive work due to the spring force, this force, or is it negative work? How do you know? How do you find that out? Well, the direction of motion is there, and the spring force is opposing. So it's going to give us negative work. All right. So we plug all this in, half times 2,000, 20 squared, and we have minus 800, 10 to the 3. We take that out, and then we integrate. So we'll integrate between 0 and x, okay? And we integrate x to the half. We know we're going to get x to the 3 over 2 over 3 over 2 equal to 0. So this becomes 400 1000 minus 533333 x to the 3 over 2 equal to 0. And then solve for this, and you'll end up getting, so you've only got the one unknown, you end up getting x is 0.825 meters. Alright? So, what did you have to learn? Non-constant force. It's the only force. You need to keep it within the integral. And then, is it a positive or negative work? It is negative because the vectors are opposing. And then you solve. Okay, cheers.